Okay, so we'll get started today. Just before we begin the lecture, just a few announcements. So the first announcement is about the next homework. So homework for, well, the homework for week 6 won't be due until, so it's available. I posted it on the website yesterday, but or maybe Sunday, but it won't be due until March 16th. So I figured, and you can still welcome to finish it this week and sort of turn it in on March 2nd if you prefer to have a break so with the midterm week and the week after without having any homework. But I figured I'd give you the flexibility to just decide yourself whether you prefer to have the sort of break now or how you want to use your time. So the content sort of hasn't changed from what it was going to be. But anyway, the content is sort of also it's sort of an introduction to some of the ideas we'll be exploring more after the midterm. So and it's a single exercise with 14 parts. So it's sort of a long exercise, but developing sort of just an interesting formula and building up some ideas. Hopefully it's not too bad. I tried to, it's supposed to be more, it's not supposed to be too difficult. So I tried to provide lots of detail in the steps, but feel free, if you end up having questions about it, feel free to ask about it in office hours or email me or what have you. Okay, so that's the first announcement. So I just want to point that out because previously I think at some point I said it was going to be due next Tuesday, or you may have expected it to be next Tuesday. And so I just want to point out the change in due date. Then there are these rewrites for the problems. So they're due next week. So I guess 4th. Right, March 4th at 11:59 p.m. So that's the day of your midterm still, no change there. But so the new information is, I previously had said to submit them via email, but actually, if possible, I'd prefer if you'd submit them on Gradescope. So I added an assignment where you can submit them on Gradescope. And if you don't have to submit anything if you don't have anything to submit or don't want to submit rewrites. And so you only submit the problems you have. And grades, it'll just be easier for me if you submit them on Gradescope. So sorry for changing that. I just had a reflection on how I was going to maintain my gradebook. Okay, and then the last thing is, so the exam, I just want to give you a little bit of information about the exam on Thursday. So I'm going to ask that unless you have a reason that you cannot, that you take it during the regular class time. So I'd like, So and same standard time. So next Thursday from 12:25 p.m. to 1:45 p.m. We'll come in here. I will put you all in sort of in individual breakout rooms. The exam is going to be just true or false and very short answer questions. And so you'll submit your answers on Gradescope unless there's an issue with your upload on Gradescope. And you can sort of, when you submit to Gradescope, you can write out your answers on a piece of paper and take a picture and upload it, or you can sort of just write it in a text document or a PDF and sort of upload that, whatever works. And if for some reason we're having troubles getting Gradescope working, if you're having troubles uploading it, you can also email it to me. But that's so you won't be submitting the work to your problems. You'll only be submitting just the answers. It should be, so you can do all your work on a piece of paper or whatever, and just then sort of put your answers in a form that you can put in Gradescope at the very end and upload that. So that part should be bad. You'll have an hour for the exam, and then we'll leave a buffer of 20 minutes or however. How long is this class? 20 minutes. I will leave a buffer of 20 minutes to make sure you don't we have time if there are any difficulties with uploading it. Right. So and yeah, and again, if you're in the classroom, then well, and I'll just post at the start of the class, I'll post the PDF on the website so everyone can access it. And then if you're in the Zoom, then you'll be able to we'll put you in your own breakout rooms, and then you'll be able to call me in if you have a question about any of the statements or anything. And what else do I want to say about that? Right, it'll be open book, open notes, but please work on it individually. And everything I just said about the exam is all contained. Like if you look at the handout for this week, sort of in the preview of next week's section, all this information is there as well. Okay, are there any questions about any of these three things? Okay, great, and feel free to email me or contact me otherwise if you do end up having questions. And then let me just say on Tuesday, so on March 2nd, we'll just do review / questions and answers. So, and basically it'll be like the class period on March 2nd will be like an office hours. So if you have questions, please come and ask those questions. Otherwise, if sort of people don't have questions, then I'll summarize what we've done. But probably you'll get more out of it if people have questions. So and think about whether you have any questions, anything you didn't understand fully, anything you'd like to understand better, and so bring those questions on March 2nd. Okay, so yeah, so now I should say, any questions about any of these things? Okay, great. So on to the math. So in this week, sort of a bridge between the first and second half of class, the first and second halves of the class. So the first half of the class was all about sort of just abstract group theory. We spent a lot of time talking about just like the structure of finite groups and sort of how you use group actions to understand that. And then the second half of the class is about Galois theory and representation theory. So there's sort of two subjects where you use group theory to study. You use the fact that groups encode symmetries of objects, and you use sort of group theory to like deduce properties about the objects themselves, and some sort of mix between the two. You can also, we'll also see examples like where we use representation theory to prove things about groups, but sort of vice versa. Okay, so the subject is characters. Okay, and so what is a character? So let G be a group. And L a field. So e.g. G could be Z mod NZ, and L could be the complex numbers. Okay, and then so then a character of G with values in L, or sometimes we'll say an L valued character of G, or if L is the complex numbers, sometimes people just say a character of G, is a homomorphism from G to the units in the field, which is just another way of saying GL1 of L. So just invertible 1-by-1 matrices, or just units in the field. This is also just all the non-zero elements of L because L is a field. Okay, and maybe recall that a field is just a ring where every non-zero element is invertible. Equivalently, a field is a ring where the only ideals are the zero ideal and the ring itself. Okay, but well, you can just for today, if you just think about the complex numbers, you'll be fine. Okay, so exercise, just to get us warmed up. So what are the characters in this example? So what are the characters of Z mod NZ with values in C star, with values in C? So the homomorphisms, Z mod NZ, C star. So here, there's like, when the definition of character, the units of your field are considered a group under multiplication. Okay, so everyone take a couple of minutes and just think about this, and then we'll discuss. Okay, so can someone offer me an answer or a partial answer? What's that? Oh, okay, great. So let me interject slightly there. So you said there are phi of n choices of an nth root of unity. So that's true if you send one to a primitive nth root of unity, like sort of a nth root of unity that's not a root of unity for sort of some smaller n. But here, in fact, you could send one to sort of any nth root of unity. So there are, yes, there are n choices. Great. Okay, good. Okay, well, good. But then this is basically the answer. So then the only sort of question is sort of how you deduce this is everything, but this is something we can do. So let's say this. So okay, so this is the first sort of basic observation you have to make, and then the rest is sort of just doing a computation. So this element 1 in Z mod NZ, it has to map to an nth root of unity. So why? Because sort of n times, why? Well, n times 1 is 0. So it's the trivial element in Z mod NZ. So the identity in Z mod NZ. And so if sort of phi from Z mod NZ to C cross, let me write this actually, chi. We often use the letter chi for characters. So if chi is a character from Z mod NZ to C cross, then chi of 0 is equal to the identity. So this is always a little bit sort of, this is always an easy place to make a mistake, is sort of when you have one group where you're writing the identity as 0 and one group where you're writing the identity as 1. But sort of sends the identity to identity, so chi of 0 has to be equal to 1. But that's chi of n times 1. Has to be 1. But chi of n times 1, well, that's chi of 1 to the nth power. So chi of 1 has to be an nth root of unity. So this is, again, sort of here, n times 1 just means add 1 together n times. And like when you apply this group homomorphism, sort of, well, the group law here is addition, the group law here is multiplication. So sort of this addition n times becomes multiplication n times. So that's why this turns into a power. But again, just sort of unraveling what are the group laws here. So chi of 1 is an nth root of unity. I mean, conversely, and for any nth root of unity, there exists a unique, so that's what this, sorry, I don't know if I've used this symbol before, but this is there exists in this exclamation point after it means unique. So this means there exists a unique chi from, so let me say for any nth root of unity zeta, there exists a unique chi sub zeta, a homomorphism from Z mod NZ to C cross such that chi zeta of 1 is equal to zeta. And this is essentially, and if you think of, so and Z is the free group, like Z is the free group on one generator. So to give a map from Z to C star is just to give sort of an element of C star, which is sort of where 1 goes to. And sort of saying this maps through Z mod N, this factors through Z mod NZ is exactly the same as saying sort of chi, that N goes to 1. So that's sort of an abstract way to think of this. I mean, you don't have to be that abstract to see this is true. Okay, so those are exactly, so these are exactly the characters. They're just, you get a single character for every nth root of unity. Well, and I mean, this is a polynomial of degree n, and so it has sort of n roots, and really like there are n distinct roots of this polynomial. Right? And what are, and just recall the nth roots of unity in C star. Well, let me describe them explicitly because this is sort of helpful to do if you're rusty or haven't thought about this in a while, or maybe never thought about this, depending on your background. So but let's be careful. So suppose zeta to the n is equal to 1 for some zeta in the complex numbers. Well, then the absolute value of zeta to the n is equal to absolute value of 1 is equal to 1. And so, well, the absolute value of zeta is equal to 1 because absolute values are positive real numbers. So you deduce that zeta is in the circle. So this S1 is equal to this, just the circle of all complex numbers with absolute value 1. And it's a subgroup. So the circle, sometimes we'll call this U1. And this is a subgroup of the complex numbers with of the non-zero complex numbers under multiplication. Good. So that's step one. And well, I mean, each zeta, like any, if zeta is, so since zeta is an S1, we know there exists a unique theta between 0 and 2 pi, they're not inclusive on one end, such that zeta is equal to cosine theta plus I sine theta, which is equal to either 2 pi I times theta, e to the I theta, sorry. This is Euler's identity. Okay, so just an out loud reminder, depending, and some of you might not have taken an advanced complex analysis class, and probably you saw this in any complex analysis class, but maybe it's good to sort of have a refresher depending on what you think. But what does this mean? Well, the exponential function has on the real numbers, it's expressed okay, you take the exponential function however you define it. There are sort of different ways to define it. And then however you define it, you sort of can write down a convergent Taylor series for it at 0 that sort of converges everywhere in the real numbers. But and if you write down that power series defining of the real numbers, that also converges for every complex number. And so that defines a function on complex numbers. That's how you exponentiate. That's how you take e to a complex number. On the other hand, if you look at that power series, and you can also sort of find a power series representation of cosine and a power series representation of sine. And if you look at the power series representation for e to the x, and then you plug in sort of I times theta, well, what you get is exactly sort of the sum of these two power series. So cosine theta, the power series for cosine theta plus I times the power series for sine theta. So this is sort of one way you can deduce Euler's identity. Okay. Now, then the key point here, the key point I wanted to make is the exponential function sort of still satisfies the additivity. So e to the z1 plus z2 is equal to e z1 e z2 for any z1, z2, and c. This follows from the property. Well, again, there are different ways you can say this, but you can check this identity sort of at the level of the power series is one way you can see this, or you can sort of deduce it from the fact that it holds for real numbers, and from the fact that it holds for real numbers, you deduce that it holds sort of formally for the power series, but then it also holds for complex numbers. So anyway, this additivity property still holds. So in particular, we get e to the I theta to the n is equal to e to the I n theta. And so this is equal to 1 if and only if n times theta is a multiple of 2 pi. Okay, and so if you look at sort of theta between 0 and 2 pi, that's exactly, so sort of zeta, if it's an nth root of unity, so zeta to n equals 1, if and only if zeta is equal to e to the 2 pi I k over n for 0 less than equal to k less than equal to less than equal to n minus 1. So, I mean, there are different ways. I mean, of course, there are different ways you can sort of show that there are n possibilities. And you can show that the complex numbers are algebraically closed. So sort of every polynomial has sort of splits into linear factors without doing this computation. And if you know that, then you get sort of this zeta, zeta to n minus 1 has n roots, but possibly repeated with multiplicity. But and there's a simple computation you can do to see that you don't get any multiplicity here. And so you have to just see that you don't have a root that also sort of is a 0 of the derivative. But for this specific polynomial, that's well, and for any polynomial, it's sort of a simple computation. For this one, it's a really simple computation. Okay, so this doesn't have any repeated roots. And so that's another way you can deduce that there are sort of n. It's sort of nice to have this sort of in concrete series expression for these nth roots. It's sort of nice, and so this is a good thing to remember. Okay, and so okay, so for each. And if I think about this, instead of sort of thinking about k in between 0 and less than equal to n minus 1, I can think about k in z mod nz. Because if I sort of replace in this formula k with a multiple of n, then I'm just sort of changing this thing by sort of multiplying by e to the 2 pi I, which is 1. So I can sort of think of it instead of having this, I can think of it like this. And in fact, so let me just point out in the characters. So this, yeah. Let me write x of z mod nz. So these are equal to the c valued characters of z mod nz. Let me note sort of this is a group. So if you start with any group, in x of g is the characters of any group g form a group. You just multiply two characters, like so chi1, chi2 of x is equal to chi1 of x times chi2 of x. So you can check that sort of this really turns the set of all characters into a group. The identity element is just the character that sends everything to 1. Okay, and so what we've just said is that the characters of z mod nz are isomorphic to z mod nz. So here we send an element k in z mod nz. This corresponds to the character, so I'll write chi sub k. So chi sub k of some other element in z mod nz is just e to the 2 pi I x times k over n. Which is equal to e to the 2 pi I k over n to the x power. So this is the character that sends 1 to e to the 2 pi I k over n. Okay, so this is sort of fun. We have an identification of the characters of z mod nz sort of as a group with z mod nz. Okay. the complex valued characters. I mean, so this will be true actually sort of, I mean, you could take characters in sort of any algebraically closed field of, well, if you know it's word of characteristic co-prime to n, and you would get the same thing, but there sort of might not be a canonical identification. Here we really have sort of a natural identification because we had sort of this natural analytic way to parameterize the n through c unity. For a general field, like you don't sort of have a natural, you don't have a natural way to pick a primitive nth root of unity, but here we did. Okay, so this is sort of all over the place, but that's the example. So the characters of z mod nz, they form a group, and that group is actually isomorphic to z mod nz, and sort of you really have an explicit formula in terms of the exponential function of all of these characters. Okay, let's do another example that was on your homework. It was as a problem on your homework, so it's fine if you haven't done it. So let's do the characters, the continuous characters of S1. So again, by S1, I just mean the complex numbers. So it's a circle, but it's a circle of complex numbers such that absolute value of z is less than or equal to 1. And so, in fact, you can show sort of any such character. So we valued in the complex numbers again. So any homomorphism chi from S1 to C star factors through S1. So in fact, you can't, like, it doesn't just map S1 to C star, it maps S1 back to itself and is of the form z maps to z to the n. Okay, and if you think about how these multiply together, I mean, again, characters of any group form a group of themselves. So the characters of S1 are isomorphic to z as a group. So n matches up with z maps to z to the n. Okay, so this was on your homework, and one way, this is not the only way to prove it probably, but one way to do this is to compute the characters of the real numbers. So the continuous characters, continuous. So, well, how did I get? Okay, sorry about that. So the continuous characters of R, well, these are all the form chi lambda. Well, let me say it this way. There's all the form t goes to e to the lambda t for some lambda in the complex numbers, not the units, the whole complex numbers. And if you do a different value of lambda, you get something different. You might, and when you look at this, you might think, like, if I change lambda by and some people made a big mistake. Some people submitted this problem and made a big mistake on it, where they said sort of the character only depended on sort of lambda up to sort of shifting by 2 pi I. And sort of the way you make that mistake is by sort of thinking that sort of the value, that the character is determined by its value at t equals 1. So like the value at t equals 1 sort of doesn't change if you sort of shift lambda by 2 pi I. But so the value at t equals 1 doesn't determine everything. So we really sort of, these are all different maps for a different lambda in the complex numbers. And in fact, this is really all of them. So characters of the real number are a group, and that group is the complex numbers, so with addition. Because so if you add together, like e to the lambda 1t, so why do you get plus here? This is just because e to the lambda 1t times e to the lambda 2t is equal to e to the lambda 1 plus lambda 2t. So the same multiplicativity property that we use when we were talking about characters of Z mod NZ. I'll come back to this example in a minute. Let me know, I mean, this was a little bit of an unfair problem to put on the homework. This problem is, it's not unfair, but if you know a little bit of algebraic topology, then this problem is much simpler than if you don't know a little bit of algebraic topology. So I probably should have put a note about that when I put this problem on the homework. So my apologies for putting a note about that. Okay, good. So these are some examples. And you might ask, I did this sort of funny thing where, and first I defined the characters just to be group homomorphisms. And then I did like one example with a finite group where I sort of used that definition. And then I did sort of two other examples where I didn't just look at all group homomorphisms. I really looked at I had sort of something that had some topology, like sort of the unit circle, sort of the topological space, and the metric space, it's a subspace of the complex numbers. And I demanded that sort of my character not just be a group homomorphism, but actually be a continuous function as well. And I did that sort of in this example too. This is something you often do when you have this structure. I mean, when you're doing math, like if you're trying to investigate something, you always want to use all the structure you have. Like here, like in S1, like if you don't treat it as a top, like there are more characters if you don't treat this as a topological group, I think. Yeah. Somehow the proof definitely completely fails if you sort of don't treat this as a topological group. So if you don't like look at continuous characters. So somehow, to get a nice answer here, you want to use the extra structure that this is a topological space and like only look at continuous characters. But somehow if you're interested, like for natural problems, we're interested in this group, like you're never going, for a natural problem about this group, like a character you're going to see is going to be continuous. Like otherwise, and somehow the circle group doesn't show up like unless you're doing like geometry anyway. Like and somehow you only are going to like in the real world, you're only going to encounter continuous characters. So this is a natural thing you do is sort of when you're encountering like groups like S1 or R or like GLN of R, like you don't just think of those as being abstract groups, like you think of those as being groups equipped like with some topology or like the structure of a differentiable manifold, and you sort of study them in that way. And the reason you do that is because like when these groups show up in nature, sort of like they show up in nature by acting on things, and when they act on things, like they always are going to act sort of compatibly with their topology. And so this is the part of the group you actually care about, the group with its topological structure. And we won't see much of that in this class, but like if you do any more math besides, as long as you don't quit mathematics now, like sort of that's something you'll run into all the time. Okay, so these are some examples of characters. So let me talk about Fourier theory. So there are different setups you can do Fourier theory in. Let me do the simplest one. So I want to describe, and this gives, okay, let me sort of do the like hand wavy definition of Fourier theory. So hand wave, if I have a periodic function on the real numbers, so like that would look like here's the real numbers, and like here maybe my period be 0 to 2 pi, and then so my function sort of looks like, well, that's not a function. Try again. So it does something between 0 and 2 pi, and then it just sort of repeats that thing Okay, and now you really get a test of my artistry, okay, and so on. So it's just repeating itself between 0 and 2 pi. And what Fourier theory does is sort of decomposes this into well, let's say this way, into its fundamental waves. So by wave, fundamental waves, I mean sort of they're like sine and cosine waves. So like a sine wave. So you look at like the function sine of n times x and cosine of n times x, where you sort of m times x, and you sort of let yourself consider all n and m. And what you do is sort of you say, okay, well, and first I should take like the constant function. So that's cosine of 0 times x is sort of the constant function 1, and I should sort of take some multiple of that. Let me say. So you want to sort of decompose your thing into sort of, so here, like, and if I sort of look at the average value of this function and subtract it off, then when I sort of take that average value, subtract it off, now my sort of wave is going to be concentrated on the x-axis. And then I can sort of look at sort of the next sort of fundamental frequency, and I can sort of subtract off sort of like some multiple of cosine of x or some multiple of sine of x, and sort of try and sort of like eliminate like some of the peaks, like eliminate sort of the dominant peak using sort of sine of x or cosine of x. Okay, so I might sort of take this and okay, I've subtracted down, and sort of then I want to sort of like do some multiple of sine of x that sort of will get rid of this dominant peak and sort of bring everything down. And okay, and I repeat and repeat, and I sort of keep on subtracting multiples of like these fundamental waves until sort of I get the 0 function, and I look at what I've done, and sort of what I've done is like I've expressed the function I started with I've expressed the function I started with as sort of a series in terms using the sine and cosine function. So sort of express a periodic function as sort of the sum of alpha I sine n x sine I x alpha k sine kx plus beta k cosine of kx. Okay. So where alpha and k and beta k are sort of the real numbers. So like this is a fundamental idea in like signal analysis. It's also called harmonic analysis, sort of. If you're a musical person, you're sort of breaking down a sound wave into like its fundamental tones. Okay, and why is this a useful thing to do? Well, and this is really something I don't know historically, but like at least ahistorically, like you would think of this as sort of coming straight at you from nature. Like why this is a useful thing to do. And I mean, like how do we make sound? Like we have like these like little vocal cords in our mouths that are vibrating, and sort of they're vibrating at different frequencies, and sort of there's some like overlap of these different frequencies, and sort of these different like if I sort of just isolate like a single frequency, this is sort of some sine wave or cosine wave of sound coming out like of sort of one of these compression waves. So like the air is moving like this in some cosine wave, and then sort of to get richer sound, and I'm somehow magically like using my mouth and vocal cords to sort of combine these different waves in some way. And really I'm sort of all these sounds are sort of built out of these vibrations that are sort of stacked on top of each other. And same with like musical instruments. I mean, you're vibrating sort of something at different frequencies and sort of overlapping some different frequencies. And Okay, and so like what that's telling you is that the natural way to describe a function, that's like the natural way to describe like a function that's like sound, like the natural way to describe sort of the waveform of a sound, or like of light, or sort of in things you measure in nature, is not by sort of like writing as a function and saying, okay, saying like f of 0 is this number, like f of 2 is this number, like f of a half is this number, f of 3 is like this number. Like you don't want to sort of say, here you take f of, like that's not how you want to describe it. You want to say, I'm combining like this wave and this wave and this wave and this wave, and I've got like 4 or 5 waves, and that's everything. And like this is actually like really like true. Like if you sort of do Fourier analysis on like the kind of like information you get out of nature, what you find is like these coefficients get very small very quickly. So basically, like they're like, like maybe there are 5 or 6 sort of dominant terms where you have like a reason, and then like all these other alpha k and beta k are very, very small. And so you can basically, they're basically not contributing, you sort of forget about them. And so this is a way to sort of go from sort of information that seems sort of arbitrarily complex to sort of just isolating the sort of important information in it. But this is also, and this is how, this is like how JPEGs work. Like if you want to know why your JPEGs are smaller than your, I don't know, bitmaps or whatever on your computer, like it's just sort of like there are two. And, okay, this sort of dates me because maybe these aren't file formats anyone uses anymore. But like bitmap is a file format for storing images on your computer, and it says like here's a grid of pixels. Like let me tell you what color every pixel is. So it's sort of like describing a function by saying what its value is at every point. JPEG sort of takes that and says, well, that's kind of a bad way to do it. I'm going to split first the color. Let me split the color into red, green, and blue, and then I'm going to take sort of the red part of the picture, and I'm going to sort of just write that, decompose it into waves, and then I'm just going to remember, like, I'll just remember the dominant terms for those waves. Like I won't remember sort of all of them. I'll just remember, like, I'll see how far up I need to go until sort of the coefficients are getting very small, and that's what I'll remember. And then it does that for green and blue too. Okay, and then I don't know. Like it turns out the pictures we like to look at, like it doesn't take very long to get down to sort of there aren't that many dominant terms, and like this takes a lot less space to remember sort of what these sort of dominant waves are, and then it does to remember the whole, like what every single pixel is, and like you don't lose much by sort of forgetting sort of the smaller order terms, like in terms of visual quality, just because sort of these sort of minor perturbations. I mean, sometimes it even looks better when you forget these minor perturbations, because those are sort of oftentimes just noise. Okay, so what does this have to do with characters? So let me sort of say this. So what does this have to do with characters? Okay, well, so step one, a periodic function. So periodic function. And there's some version of this and if I have time, I'll say some about what you do for non-periodic functions, but it's sort of, the analogy is not as tight, so I'd have to be more careful. But so let me just do sort of these periodic functions. So a periodic function with sort of period 2 pi, so that just means it repeats sort of every time you go 2 pi. Well, this is the same as a function on S1, because I can sort of write the real numbers mod 2 pi times z. That's isomorphic to S1 just by sort of Euler's identity. So I send some x goes to e to the, or let me say t, goes to the e to the it. So this is an isomorphism. a homeomorphism between these two topological spaces that's also sort of an isomorphism of the groups. So and for all intents and purposes, I can treat these two things as the same. And so I can think of a periodic function as being just a function on S1. And then, well, I can think of sort of real valued functions like the picture I drew above. And these are just living inside of complex valued functions. And then, instead of looking at sine, like sort of multiples of sine and cosine, I can use Euler's identity to just look at sort of like cosine of sort of n theta plus I sine of n theta is equal to sort of e to the int. And then if I sort of also look at sort of, and if I also look at e to the I times minus nt, then I'm going to get sort of, cosine won't change, but cosine of minus n theta is the same as sine of cosine of n theta, but sort of sine of n theta will become minus sine of n theta. And so like if I look at sort of e to the minus int plus e to the int over 2, this is over 2i. So over 2, this is cosine. And sort of e to the minus int, e to the int minus I times e to the int over 2i. This is sine of n theta, or sine of nt, sorry, if I'm switching between n and t. So if I want to sort of know cosine of n times t and sine of n times t, I should have said sort of for all like positive numbers here. Well, that's the same as sort of knowing just e to the int sort of just for all. Now I have to let myself have all integers. But in the function e to the int, like, okay, so t goes to e to the int as a function on S1. So as a function on R mod 2 pi z. This is just the same, like after I make this identification with t goes to e to the it, this is the function z goes to z to the n on S1, which is a character of S1. So this is a character of S1. Okay. And so Fourier theory is really just two sentences combined. And so Fourier theory for S1. Okay, well, there are many different things you can say. So let me, but let me do the simplest version, which is to look at L2 functions. So L2 of S1 so this means functions f on S1 such that, so C complex valued functions on S1 or sort of on R mod 2 pi, or sort of just on periodic functions with R, such that the integral of absolute value of f squared is converges. So this is sort of really measurable functions. So just square integral functions. I don't know if you guys, probably some of you know, and probably some of you have taken basic functional nonsense, and I actually don't know what we cover in what sequence when here. So hopefully this is familiar to some of you. But if not, just think, if this is not familiar, you can just take continuous functions on and continuous functions on the circle live inside of here. Okay, and so what's the statement? And the statement is, okay, the characters in these characters, these are functions from S1 to the complex numbers. and they form an orthonormal basis. For L2. So these are functions living inside of here, and they give you an orthonormal basis for this space. And that literally means, and this is just like, okay, so this is an infinite dimensional vector space, but it has an inner product on it. So the inner product on this is an infinite dimensional vector space with inner product integral of, so the pairing of two functions f and g is just the integral of f of z times g of z bar. So you just take the complex conjugate of the value. That's one. I'm not writing, and I haven't written down what the measure is here. The measure is, let me say it 3 ways, and hopefully, if you know what I'm talking about, one of them is familiar, and otherwise, otherwise, I mean, anyway, we're trying too hard. Like, just if you don't know what I'm talking about, like, make sense of this integral the only way you can think of, and you'll have done the right thing. So here, it's just the standard, like the unit volume Haar measure on S1, or what's the same as just like the standard Lebesgue measure on the real numbers divided by 2 pi, and sort of just under the identification of like the fundamental domain between 0 and 2 pi with S1. Okay, but if you don't know any of what I just said, then just write down like the only integral you really could here, and you'll get the right answer for what I mean by this. Okay, so and this is, depending on your background, an exotic thing or not an exotic thing. This is called and this is the basic example of a Hilbert space, which is sort of where the theory of like infinite dimensional vector spaces with inner products lives, Hilbert spaces. But anyway, like it makes just like a finite, like if you have a finite dimensional vector space with an inner product, you can sort of talk about orthonormal bases. And here you can also talk about orthonormal bases. And what that means is sort of any f contained in this space can be written as sort of f of z is just the sum as a sum of these these simple functions, z goes to z to the n. Here, let's see. And if we sort of think of this, saying that f of t sort of z is equal to either 2 pi I t. Then this is saying that f of t is the sum from n contained over n contained z of an times either 2 pi I and t. An contains c, and sort of in these numbers an sort of satisfy some convergence condition. So, I mean, really, you need sort of the sum of n contains z, the absolute value of an squared. Less infinity. So if you write down a function like this and you sort of integrate its square, what you're going to get is this. So this is sort of the norm of this function. Okay. But then this is exactly, and this is set, and so this statement, which I didn't prove, so I haven't proved this, but it's actually a simple. This is basically a calculus exercise to prove. Well, a calculus, maybe there's some part of it that's like a little bit of analysis and not so easy, but like, for example, like seeing that these things are orthonormal, it's just a matter of like integrating sine and cosine against each other. Like it's a basic integration problem for sine and cosine in the end. And that's not the best way to do it, but that's one way you can think about it. Okay, and so, but this is exactly, this is sort of, you took an arbitrary periodic function and you decomposed it into sort of these waveforms. Like now if you look at, like, if you took a real function here, then you could just take sort of the real part of each of these and you'd get some decomposition into sort of sine and cosine. So and there's some translation to go, but I mean, this really, this is the sentence you can decompose these things. Okay, so yeah, so and I've sort of said what this has to do with character theory, in the sense that, like, my orthonormal basis is made out of characters. So that's sort of the idea. Maybe, okay, so I haven't given you a break yet, and it's later, so let's take a 5-minute break, and then but yeah, I guess so I was going to do this in a different order. Let me think for a second. Yeah, okay, let's take a 5-minute break, and then we'll come back, and I'll just finish this example up today, and then I will go back to something sort of living more in a more familiar world. Because what we're going to do is we're going to sort of take this example, which, well, is either helpful for you if you've sort of seen Fourier analysis before, or is like completely mysterious to you if you haven't. And sort of, well, sorry if you're in the latter category. We won't need this example going forward. It's sort of just supposed to motivate connection. But I'll finish this example and the rest of it today, and then next time we'll talk at the start of class about the analog for Z mod NZ. So you can do Fourier analysis on this finite group Z mod NZ is sort of the point. And there's will sort of, everything will sort of be sort of completely living within the world of things we already understand. We'll be connected to other interesting things. So okay, but let's take a 7-minute break, and then the last 10 minutes of class, I'll finish up this example and just say a few more things about it. Okay. Start again. No problem. Okay, so let me give you a slightly different perspective on this decomposition. So observation, so a different perspective. Well, I have like the space L2, S1 with complex functions, but and really I could look at sort of, or I could look at like C infinity, so I could look at like smooth functions, or I could look at like just continuous functions. I could look at sort of different types of functions on S1 with complex values. And so I could look at sort of all these are sort of spaces of functions on S1. But whenever I have like a reasonable space of functions on S1, so let me just call it, so let me say capital F is some space of functions on S1. And then, well, I actually have an action on F because sort of by right translation. Well, I can do that sort of other way, but let me do by right translation. So this means like if I have some Z in S1 and some function, so I have some point in the circle, and then I have some function on F. This is some function on the circle, then Z dot F of some other point X is equal to F of X times Z. So here, and this here I could replace, and this makes sense, S1 so with any group. So like if I have just any group G and I have a space of, like some reasonable space of functions on G, then like I get an action of the group on that space by right translation. So for example, like this is like we saw some version of this when we gave our sort of funny definition of the sign function of the sign of a permutation, because we said, okay, like, well, not quite. Okay, never mind. Sorry. Let me back up. That's not quite true. We did something related to this when we sort of did that. Okay, good. And so then, now sort of F is a vector space. So the complex value functions, the C vector space, and sort of the action of S1 on F is sort of bilinear operators. So there's this right translation action, like it's not just an action of sets, like it preserves the vector space structure on this space of functions. And so you can ask sort of like, so this is something called, this is a representation. So usually the first time someone tells you about representation theory, they would tell you about a finite dimensional representation. So perhaps I've taken sort of an unconventional tack. But this is sort of, this is on an infinite dimensional vector space. But it's a really nice infinite dimensional vector space. It's a Hilbert space. So it has like this inner product. And this inner product sort of is a Hilbert space with the inner product preserved by S1. Okay. And so there are some subtleties here, but basically this tells you that you can sort of write this representation sort of decomposes as a direct sum of characters. So a representation is just an action of a group on some vector space that sort of respects linear structure. And so a character, well, I said before that was a map from a group to like C star, from like G to C star, so from S1 to C star. But that's just and that's the same as saying a one-dimensional representation, because like C star is just GL1. So like acts on one-dimensional. And it turns out like what we'll see in representation theory is that at least in nice situations, if you have a group acting on sort of some reasonable vector space, a Hilbert space with inner product, sort of a pretty reasonable vector space, then that representation decomposes into irreducible representations. So you can write sort of a direct sum of sort of these irreducible objects, just like you can factor, just like you can sort of, like any of these decomposition theorems we've seen before, like you can sort of like factor a prime number into primes. You can sort of factor a representation into irreducible, or so you can factor an integer into primes. You can factor a representation into sort of irreducible subrepresentations. In this case, because this group is abelian, sort of all these irreducible representations will actually be just one-dimensional, so these characters. And if you think about it, like that's exactly sort of what we've done here. So this is sort of a completed direct sum. So this is some analytic thing related to the fact we have a Hilbert space, not a finite dimensional vector space. So you can ignore that hat if you don't like it, of sort of C times Z to the N. So all these sort of one-dimensional vectors. So this is a decomposition into subrepresentations, to irreducible subrepresentations. And so how, like the action of S1 on this function Z to the N sort of is just by the character Z to the N. So you can sort of sort this out for yourself, but so if I sort of look at, if I have Z contained in, so into T contained in S1, and then I have this function Z goes to Z to the N. Let me write this way. And this is really the function Z goes to Z to the N. So it's this character. then sort of if I take t, and I act on sort of this function by right translation, well, it's just an exercise to expand this out, and you'll see that this is equal to just t to the n times c equals to t to the n. So this irreducible subrepresentation is sort of given by this character. So what this is saying. Okay. And well, this is all very vague because I haven't been sort of this is all, we haven't sort of set up a general theory or anything, but this is sort of a nice alternative perspective on what's happening here. Is we have this vector space, this nice vector space, this Hilbert space, with an action of this sort of this group S1, and we can sort of look at how we can break down that action into sort of like irreducible parts. Just like if you had a group acting on a set, you would sort of break it down to its orbits. Here we have sort of a group acting on a vector space, sort of respecting the linear structure. So we sort of can do this thing where we break it down into sort of these irreducible representations, which are sort of like these irreducible subrepresentations are sort of like the representation theory version of an orbit. Okay, so you break it down to these things, and like that decomposition is giving you sort of the decomposition that's arising in Fourier theory. So this perspective is sort of vital to sort of generalizing Fourier theory, sort of beyond sort of the case like the real numbers and sort of S1. So this perspective is sort of the right perspective to have. And it also, like you can, sort of it shows you it's sort of useful in just if you have any vector space, if you have a group acting on a vector space, like it turns out you can get really interesting structure by sort of trying to decompose that vector space into sort of like these irreducible chunks. Like it's really revealed sort of something new about this vector space. Just like, I mean, because here, like we started sort of with functions on, where were we? We started sort of with functions on, with periodic functions on the real numbers, which like when we started this conversation, the best we knew was that sort of you had to sort of give for every number between 0 and pi, like what is the value of f of x in order to describe such a thing. Then sort of we saw, I mean, there was this better way to describe it in terms of sine waves and cosine waves, at least for sort of the kinds of functions we run into in real life. But in like secretly, what this is doing is, I mean, we're using the symmetry, like we're using some natural symmetries of the real line. So we're sort of using sort of this translation symmetry of the real line via sort of the action of S1 on itself. And then we're saying, okay, like let me sort of turn that symmetry into this decomposition that's giving me Fourier analysis. So you're doing sort of this very, I mean, somehow this process is this very important idea in math and physics, where you can sort of, and you can, like for example, you can sort of, and you can encode like the same idea using sort of different mathematical structures. So, I mean, on the one hand, we could sort of encode this by saying, well, we could encode this idea of decomposing the waves by saying we had sort of this harmonic, so we had this sort of orthonormal basis of harmonic functions of sine waves and cosine waves. But you can also sort of encode it sort of, I mean, what's special about these functions, it turns out, is sort of these are sort of some of the maximally symmetric functions for the action of S1, which is like the translational symmetry on near real lines. So you're sort of encoding this, the structure is coming from the symmetry encoded in this action of S1. And that's sort of really where like this Fourier decomposition is coming from. And this is sort of the right way to generalize it to other groups, is sort of to other groups in like other settings. It's sort of when you have a symmetry group acting on some like space, then you can sort of try and decompose the functions on that space according to like how that into like the irreducible chunks for the actions of those symmetries. And this is a very like, extremely powerful idea that sort of is like everywhere in modern mathematics. Okay, so right, so that was all over the place. And I'm over time. Let me stop here. But next time we'll do Fourier analysis on Z mod NZ, and we'll see sort of something much more concrete. Sorry for going over time.